discuss what it means for a set of vectors to be linearly independent. If we have a set of vectors, we say they are linearly independent if the equation x1a1 plus x2a2 all the way up to xn is equal to 0 has only the trivial solution. So the xn's, or the xi's, are all scalars, our a's are vectors, and we just want them to set it equal to 0 and say that we only have the trivial solution. If we have any non-trivial solution, we say the system is linearly dependent. Let's consider these three vectors. I want to know if they're linearly independent or linearly dependent. Therefore, I'm going to look at this equation, x1a1 plus x2a2 plus x3a3 equal to 0, and try to figure out how many solutions it has. And the a's here are these three vectors. Therefore, we want to set this up and solve. 1, -2, -1. 1, -1, 0. 4, 2, 4. And since this is homogeneous, we leave off the augmented column. I have a 1 in the first row, first column. I want to get zeros below it. The first one's a -2. So I'll do 2 row 1 plus row 2. That would be 2 minus 2 is 0, 2 minus 1 is 2, and 8 plus 2 is 10. For my third row, I can just add row 1 and row 3. 1 minus 1 is 0, 1 plus 0 is 1, and 4 plus 4 is 16, or is 8, sorry. Fix that. I now have a 1 in the second row, second column, and I'm going to get zeros below it. I don't need to worry about getting zeros above it because I don't actually care what the solution is. I only want to know if it exists. So all I really need to worry about is getting my pivots. I can do this by subtracting negative row 2 plus row 3. 0 plus 0 is 0, -1 plus 1 is 0, and -10 plus 8 is -2. And now I can see the pivot in all three rows and columns. Therefore, this has only the trivial solution, since I only have one solution. So these vectors are linearly independent. There are a few special cases where we can easily determine if something is linearly independent and dependent without doing any calculations. We'll start with a single vector. That means we need the solution x, a, since we only have one vector, equal to 0 to have only the trivial solution. This would give us two options. Either x has to be 0 or a is 0. If x is 0, this is our trivial solution. So we need a non-trivial solution, which would result on the other side if a was 0. Therefore, the only way a single vector can be linearly dependent is if it's 0. As long as it's not 0, it is linearly independent. And we can actually go a little bit further and say something else about the 0 vector. If we have a set of vectors that contains the 0 vector, then the set is linearly dependent. Any set that has the 0 vector in it will be dependent. And this is a fairly easy proof to follow, so we'll go ahead and show it. Our first step is to reorder our vectors so that the first one is 0. Ultimately, it doesn't matter which vector is first or second, as long as we keep it once we start the problem. So we'll reorder them so that the first one's 0. Then I have this equation, 1a1 plus 0a2 plus 0a3 all the way up to 0an, which will be equal to 0. All of these terms will be equal to 0 since they're multiplied by 0. And this one, since a1 is equal to 0. Therefore, this is a non-trivial solution. And as long as you have a non-trivial solution, you are linearly dependent. The next special case we'll look at is the set of two vectors. In this case, I would have x1, a1 plus x2, a2 equal to 0. I can subtract 1 from the other side. And since I know, or rather, since I'm trying to figure out when this has a non-trivial solution, we can assume that x1 is not equal to 0. If we want a non-trivial solution, at least one of these has to be non-zero, so let's assume it's x1. Then I can divide both sides and get negative x2 over x1 times a2. Therefore, a set of two vectors will be linearly dependent if one is a multiple of the other. As long as they are not multiples of each other, it'll be independent. But if they are multiples, we will have linearly dependent. We have one more theorem that concerns a special set that can easily be determined if it's linearly independent or dependent. If we have a set of vectors a1 through an that contains more vectors than entries in each vector, the set is automatically linearly dependent. And we will discuss next, we will talk about the proof of this. The corresponding matrix for these vectors is m by n, with n greater than m. We have more columns than rows since we have more vectors than entries. Each vector corresponds to a column, each entry corresponds to a row, and since we have more vectors, we'll have more columns in our matrix. Every column in this matrix cannot be a pivot, since we can have at most m leading entries, so then we have more columns in this. Therefore, not every column can be a pivot, and those that aren't will correspond to our free variables, which means we have infinite solutions, so we have non-trivial solutions. And non-trivial solutions means we are linearly dependent. So therefore, if I have more vectors than entries, we will be dependent. Let's look at some examples. Here I have a set of two vectors, and I can see that if I multiply this first one by 2/3, I get to the second one. 2/3 times 3 is 2, 2/3 times 6 is 4, and etc. Therefore, these are linearly dependent since one is a multiple of the other, and that was our rule for a set of two vectors. Here I have a set of three vectors, and the center one is the 0 vector. And anytime we have the 0 vector, we can automatically say that the set is linearly dependent. As our last example, I have a set of 4 vectors with 3 entries. And here we have more vectors than entries. Since we have 4 vectors, each vector has 3 entries. So the theorem told us that this set is linearly dependent, because if we try to form the matrix, we'll be forced to have a free variable. Finally, we'll look at a couple more theorems concerning linearly independent and dependent. Our first just relates linearly independence to matrices. We say the columns of A are linearly independent if and only if AX equal to 0 has only the trivial solution. We can also say that a set of vectors of 2 or more vectors is dependent if and only if at least one of these is a linear combination of the others. And finally, we'll add on a little bit to our invertible matrix theorem. Before, if we had A as an n by n matrix, the following are equivalent. Our first thing was A is invertible. I'll skip writing down the rest, and then I'll add our new 3 things. Our first, any given vector B can be written as a linear combination of the columns of A. Our next one, any vector b is in the span of the columns of A. And finally, the columns of our matrix A are linearly independent.